Alright, now we're ready to jump back to our full code for merge sort here, and we're ready to fill in the blank for the cost of a merge. I know I said that we had a change of variable, and we're going to eventually call it we're going to call it t of m. But in this outermost call, m is going to be equal to n, and since I'm dealing with n over 2 here, it makes sense to just stick with one variable, and we'll call the cost of merge to be big O of n, which should be fairly comfortable for you, because if we look at the code here again, it's just a single while loop, not nested or anything, so it's going to be a linear running time, linear based on the number of elements that we pass in. So we've got our total running time of merge sort. It's equal to 2 times t of n over 2 plus big O of n. But what is that asymptotically? Sort of, if I want to compare this to insertion sort, with insertion sort we were talking about linear in the best case and big O of n squared in the worst case. How does that compare to this up here? So again, this was for insertion sort. How do these compare? Well, to look at how they compare, we need to do a little bit more work. We need to figure out exactly sort of how much work is this t of n over 2 bit. So to do that, again, like we discussed in a couple slides back, we need to know how many times do we call merge and what's the size of each merge. So to figure that out, we're going to look at our problem in a little bit different way. We're going to look at it like this, but a little bit more abstracted. So this is sort of a call tree, and we are going to look at something called a recursion tree. So here at the top level is sort of our topmost call to merge, or our topmost call to merge sort, and it has the entire input, so all n elements, and that's going to be at level 0 of a binary tree that we're looking at. A binary tree because merge is always going to split the input into 2 equal-sized halves. At level 1, each of those 2 calls to merge sort is going to have n over 2 elements, and then eventually, when we come back up this tree, we're going to merge those 2 sets of things back together, and we'll call merge on all n elements. But we're not there yet. We're kind of going down the tree. At level 2, we've got that, well, we had n over 2 elements here. We divide that by 2, and now we've got like n over 4 elements here, and n over 4 elements here, n over 4 elements here, and n over 4 elements here. Another division by 2, and we've got n over 8. And then at the very bottom of this tree, so not at the next level, because we're using a generic n here, I'm not saying exactly how many elements we have, but we keep doing this until we get down to size 1 elements. Why size 1? Because that's our base case for our version of merge sort. Typically in merge sort, you would use a base case of like size 5 or so, and use insertion sort to sort that size 5, just to reduce the total number of calls you have, the total number of function calls you have. But let's just assume we're going to recurse all the way down to 1 element. Alright, well, what is that bottommost level? When we have a divide and conquer style algorithm that's continually dividing by 2, you're going to continually divide by 2 till you get the base case. Here our base case is going to be when the size is 1. Well, we have a special function in mathematics for saying that, okay, what happens if I continually divide by the same number over again? So that's what a logarithm is. A log is when you continually divide by the base. So we'll say that the last level here is, well, whatever you get when you continually divide n by 2. That's the label, the number of levels that we have in the tree, or it's really the label of the bottommost level in the tree. We'll always have a base 0 indexing here for our tree, so we really have log base 2 of n total levels. So the total levels on the tree is that. So that should give us an idea of how many calls to merge we have. We have 1 call to merge here, 1 call to merge here, 1 here, 1 here, 1 here, 1 here, 1 here, and we know at the very bottom we'll have n calls to merge. So let's work through the exercise. So we finally gotten to the point where we're going to start working through the exercise, and I'll stop this video here, and what you should do is now go to the course website, grab the exercise, and work through it, and see if you can do so before looking at the slides or the video. If you can't get through the entire thing, that's perfectly reasonable. The answers to all those exercise questions will be in the slides as well. But it's important to try to get an answer to them first.